All right, the goal of this particular module is to be able to solve cascaded lines. What happens if we have two transmission lines of different characteristic impedance kind of coupled one after the other? So what that would look like, we'll just draw a generic case. Probably the easiest way to go about this is to do a simple example. So let's just make a generator of 2 volts going in. So Vg is going to be equal to 2 volts. And the associated impedance is going to be 50 ohms. And that's going to go into a transmission line. And since we're going to be talking about multiple transmission lines, we're going to call this Z01, and that's going to be 50 ohms. But then let's say you ran out of 50 ohm cable, and so you just decide to cheap out and just grab whatever's available, and whatever's available is a cable that has a different characteristic impedance. So let's just call this Z02, and that's going to be 100 ohms. And you just say, how bad is it going to get? And try to get by. And then you get to your load on the other end, which we'll just say is 50 ohms. So what we want to do is solve this and draw a bounce diagram, and I'll clarify that these are actually connected. A lot of the main fundamentals that we've taught actually still ring true here. And the only difference is there's going to be this extra interface in the middle where you're going to have transmission and reflection. So the key parameters that we'll still need to be able to draw our bounce diagram, we still have our input voltage over here. We have our load voltage at the output. And as the wave goes in through, once it reaches this juncture, you will have a reflection. So I'll call this gamma when you're 1, 2, as in gamma when you're going from line 1 to line 2. And then some of it will go across. So there's going to be a tau 1, 2. So some of it's going to go across, some of it's going to come back. And then the reflected wave is going to go back in this direction. The transmitted wave is going to continue on this way with this characteristic impedance of 100 ohm. And since it is not equal to the load impedance, once you get here, you will also have a reflection. So over here, they're going to have a reflection. That's going to be gamma load. And you're also going to have a portion of it go across, which is going to be the amount that goes there. But wait, there's more. Once this wave goes back, what you're going to see is you're going to hit another junction over here, right? And since there's a mismatch, some of the reflection is going to happen over here. So I will call this gamma 2, 1. So the reflection from gamma 2 going into 1, and some of it is going to go through. So there's going to be a tau 1, 2. I'll just draw that here. So there's also going to be a tau 2, 1 going from 2 to 1. And this is a lot of parameters to keep track of, but remember that the key thing that you have to remember is still that gamma is going to be equal to new minus old and new plus old. And the other thing to remember is that the transmission is going to be equal to 1 plus gamma. So I'm going to write a bunch of math, but really there's all these different gammas, but the formula remains the same. It's new minus old over new plus old, and then the transmission is just 1 plus gamma. So you just write down all the key values and evolve your bounce diagram, just bounce away, and every time you hit an interface, you reflect part of it by multiplying it by the corresponding reflection coefficient, and then you have a part of the wave transfer through and use the transmission coefficient to figure out what that is. So let's start calculating our key values before we start drawing some pictures. Oh, and one last thing, just to keep the bounce diagram sane, we're just going to make these the same length. because if we don't, it will just make life really miserable. But I think that with the same length, you can kind of get an idea of what's going on. So let's start by calculating all of our necessary values that we need to draw the bounce diagram. So start out with, I usually like to start with just figuring out what's going in, which is going to be your initial V plus, and that's going to be the voltage divider here. So you have 2 volts over Z01 over ZG plus Z01. And since these are both 50 ohms, so you end up getting half the voltage going in, the answer is going to be 1 volt. So that's going to be your initial voltage going in. And next up, we're just going to calculate a boatload of coefficients. Let's start with gamma going from 1 to 2. You're going to really know this formula by the time we're done with this. So gamma from 1 to 2, remember nu. In this case, we're going from 50 ohm to 100 ohm. So nu is 100 and old is 50. So 100 minus 50 over 100 plus 50. Or since we're starting out, I'll just be more explicit. It's Z02 over Z01 plus the sum of the two. And that's going to be equal to 1/3. Next up, the amount that's going to transfer across, that's just going to be equal to 1 plus gamma 1/2. So that's going to be equal to 1.333, or 1 1/3. Next up, the reflection coefficient from 2 going to 1 is going to be equal to Z01 minus Z02 over the sum, which is going to be equal to minus the value here, which is nice and convenient. And tau 2 going to 1 is still going to be equal to 1 plus gamma 21, so it's going to be equal to 2/3, 0.666. And then let's calculate some values at the load and at the generator. So on the generator side, we can just eyeball it. These two have the same impedance, so when you take the difference, it's going to be 0. So you're matched at the generator side, which is good. That means that there will be an end to all the waves bouncing around eventually. And then this gamma L, the reflection at the load side, is going to be equal to nu minus old, nu plus old, is going to be 50 minus 100 over 50 plus 100, which is going to be equal to minus 1/3. So with these parameters, we can now start drawing the bounce diagram. So what I like to do if I'm faced with a hairy circuit is to just make sure that I outline all of the necessary parameters that I have to calculate, and then I just work them all out one at a time. And then now I'm armed with all the information I need to draw the bounce diagram. And these transmission lines are the same length, so thank goodness I say. Let's just draw. This is going to be the first segment over here. This is going to be, so this is the first segment, this is the second segment. We're still going to use the capital T as the amount of time it takes to do one trip. Let's go up to 4T, and I'll just add these dashes over here. Make sure that has some semblance of neatness. And then it's also good to summarize the key parameters over here, just so that you don't have to dig them out from all those calculations that you had earlier. So gamma L equals minus 1/3. And over here, I'll just summarize that going 1 to 2 is 1/3. Tau 1, 2 is going to be 4/3. Gamma 2, 1 is going to be minus 1/3. And tau going from 2 to 1 is going to be 2/3. And now you just have to propagate away and make sure you don't mess up. So let's just start with our initial wave going in. I'm going to just worry about the voltages for here. The main goal that I'm going to have is just make sure that you know what to calculate. But the concepts that we've talked about before apply. So if you want to know the voltage at any point in time, you just add up every transition, every line you cross, you change the elevation of that particular triangle slice accordingly. So you can ultimately still work your way to figure out what the voltages are at any point. And if you need the current, remember the same rule applies, divide it by Z0. If you're going in the right direction, if you're going to the left or the negative Z direction, then you don't forget to add a negative sign when you divide by Z0. So then you can find the current everywhere after I calculate these voltages. If you need the power, then it would just be the voltage times the current. So remember our first wave going in is just going to be 1 volt, which we calculated over here. And then we hit here and a portion of it goes through, which is this 4/3 here. So this is going to be 4/3 of a volt going here. And then a portion of it's going to reflect. And the portion that reflects is going to be 1/3 of a volt. And now when it gets here, remember our gamma G is equal to 0, so it gets absorbed and we're happy. Now when it gets to this load side, a portion of it is going to go to the load, the other portion of it's going to reflect. The amount that reflects is this minus 1/3 here. So you're going to have you're going to have 4/3 times minus 1/3. That's going to be the voltage that reflects back. And then once you get to this interface, a portion of it transmits across. The portion of it that transmits is this 4/3 factor. Oh, this 2/3 factor. Apologies. So you multiply it by tau 21. So that's going to be equal to 4/3 minus 1/3 times 2/3. And I'm just going to keep them separate like this so that you can actually see what numbers are being multiplied. And then a portion of that, the other portion of that is going to get reflected. And so that's going to be equal to 4/3 minus 1/3 times this reflection here. So minus another 1/3. And so doing that back and forth, you can keep going until ultimately what you'll see is there's a lot of reflections going back and forth here. And then every time a portion of it transmits back to the first transmission line and gets absorbed by the generator side, where you have a nice match. One last thing that I want to reiterate is that we can use the Thevenin equivalent to convert any of these waves into what's going into the second transmission line from the first one. So using this tau parameter, we're able to do it, but I also just wanted to demonstrate really quickly that we can also use the Thevenin equivalent to do the same. So for the equivalent portion of the junction, remember the Thevenin equivalent, say we wanted to look at what happens with this initial V plus wave that goes in. Don't forget that we can also just set it as 2V plus as a generator with the characteristic impedance of the transmission line as your source impedance. And then remember, because of transmission line theory, you don't really see the load, you just see the transmission line, the characteristic impedance of the transmission line in front of you. So you're going to have Z02 here. And so this is your Thevenin equivalent circuit. So you can use that to solve for the voltage that's, we'll just call this V smiley face, because I'm out of letters right now. This V smiley face, you can just do the voltage divider of V plus Z02 over Z01 plus Z02. And this is equal to 1 volt. And these are 150 respectively. So you're going to find that that is equal to 4/3 volt. And note that that result is the same as this over here, which we also got by just doing 1 plus gamma from 1 going to 2 times V plus. And so regardless of whether you're doing the Thevenin equivalent or the 1 plus T or the Thevenin equivalent situation, they should both give you the same result. Just keep in mind that the Thevenin equivalent is a way that you can, again, convert any wave that's exiting the transmission line and figure out what it is outside of the transmission line. Sometimes when you have really complicated situation, being able to substitute it with this makes it a little bit easier to think about. Now, before we wrap up, let's add one more level of complication, which is what will happen if we add some circuitry in between these two transmission lines. How would we deal with that? Well, first of all, I can't fit all that, so let's just start with a new board. And the answer is, if we add some circuitry, it just changes our equivalent of the transmission coefficient when we're going from one direction to another. So I'll just do one example in one direction just to illustrate the process. But you're basically just going to add another factor in your transmission coefficient. So let's just say this is the first junction, and then we're going to add a series resistor, R1. We're going to add a shunt resistor, R2. And then we go into the second transmission line. So in our prior example, this was just straight connected through. Now we're going to add a series and shunt resistor. And then we're going to call the input into the second transmission line as VJ2. So VJ1 is the voltage at the output of the first line. VJ2 is the voltage going into the second line. So what we want to do is we want to try to calculate a tau f. So something that relates VJ1 to VJ2. In other words, to clarify, instead of just having the tau 1 to 2, we're going to replace that with a tau f that not only takes care of the reflection coefficient and so on, but also takes these resistors into account. So to do that, let's start by, first of all, since VJ2 is going to be the voltage drop across this transmission line as well as R2, let's just define a parameter. Let's let RP, or R parallel, to be equal to R2 in parallel with Z02. Because for the wave that's going this way, it just sees Z02. It doesn't see anything else that's coming out on the other side. And so written out completely, that's going to be R2 Z02 over R2 plus Z02. So that's going to be equal to RP, which we'll simplify our math further on. And so now what we want to do is we want to relate the two junctions. So VJ2 is going to be simply a voltage divider between R1 and then this equivalent resistance RP. So VJ2 is going to be equal to VJ1 times RP over R1 plus RP. Now remember, we also want to write VJ1 in terms of the wave that's coming in, right? Because what we want is, we just want this tau f to be just something that you multiply into whatever wave is trying to get from one side to the other. And once you find that tau f, you can use it the same way you were using tau 1, 2 earlier, and forget all this ugliness in between. So let's write VJ1 in terms of the rightward going wave. So remember that VJ1 is going to be equal to tau from 1 going to 2 of the wave that's going to the rightward direction, and that is also going to be equal to 1 plus gamma 1, 2 V plus. So let's just write, let's just go ahead and substitute that into here. So we're gonna plug that into there. So now we get VJ2 is going to be equal to V plus, and then 1 plus gamma 1, 2 times RP over R1 plus RP. And so now, remember, our ultimate goal is to figure out what this is in terms of V plus. So we want Vj2 is just going to be equal to tau f V plus. That's how we want to end up using this tau f, which means if you're comparing the two, then this whole thing over here is our tau f. And so tau f is going to be equal to 1 plus gamma 1, 2. And this is what tau 1, 2 used to be. But with this circuit, we just add this extra factor of RP over R1 plus RP. And so that is what you would use in place of tau 1, 2. And remember, you would have to go back and do the same thing to find the equivalent of, I'll just call tau back, where you're relating Vj1 in terms of Vj2, but the process is very similar. And then you would then relate that to the V minus coming in. And once you find these two values, you just put those in your reflection diagram, and then it's the same as the situation when there wasn't any circuitry in between.